Okay, so it is the 28th once again. Okay, so we're talking about ionization energy here. And ionization energy is how much energy it takes to remove an electron from a neutral atom. And on your periodic table, you should have that periodic table out in front of you at all times. Put your finger on the group that has the highest ionization energy for its period every time. Highest ionization energy. Put your finger on it. Compare where your finger is to where your compatriots' fingers are. Which group has the highest ionization energy in its period? I see people who are a little uncertain. I see some of this. That's okay. That's okay. Pin the tail on the group. How many of you have your finger on group 18, the noble gases? Okay, good. Or you're tapping it with your pencil, you know. If you don't like to follow directions literally, that's okay. I'm fine with that. Yeah, because those noble gases are perfectly stable. They've got a full upper S&P. They don't want to give up any electrons. They hold on to them very, very tightly. They tend to have the smallest radius in their period, and they tend to have the highest ionization energy. Is this a coincidence? No. What causes that small radius? What causes that small radius? Discuss it at your table, briefly. I heard a few people say things about tightly held outer electrons, because without adding any energy levels, you've added electrons to the outer level, and you've added protons, and so you've got this increased force of attraction between the nucleus and that valence level. Well, if they're pulling more tightly, if they've got a better grip on those outer electrons, it also means they're harder to strip away. So when we see high ionization energy, we tend to see low atomic radius. They are related how? Directly or inversely? Talk about it at your table. Directly, is that a direct relationship or an inverse relationship? What? I didn't know there'd be math terms. That's totally bogus, Moser. It's a Tuesday morning and I've slept in for 6 days in a row. Hopefully you all slept in for 6 days in a row. What kind of relationship is that? Who would say inverse? I would. You should vote with me. I know this. Inverse means when one quantity goes up, the other quantity goes down. That's an inverse relationship. So this is an inverse relationship. There's an inverse relationship between atomic radius and ionization energy. So when you see a very low ionization energy, you would expect to see a larger atomic radius. Now, what about plucking off the second electron? Have we talked about that? I don't think we have. And if we did, it's been 6 days of sleeping in and too many carbohydrates, so I don't think you remember it anyway. Well, that's unfortunate. So once I get the next electron off, and I now only have one valence electron, and this is an aluminum 2+ ion, which you don't really see in nature. Doesn't stop there. Now we're looking at 13 protons pulling on 11 electrons. What do you think happens to the ionization energy now? What happens to it? Does it go up or down? Point. Ceiling or floor? Oh yeah. This is totally not a fair fight. Point. No, I'm serious. You people have to play along with me. Come on. It's a Tuesday morning, which is a metaphorical Monday, and I'm not stopping this nonsense until everybody points. Kinesthetics, folks. Kinesthetics. Okay. Now, and we could actually, we have purpose for the T-rexing. So the first one took, this much energy, and the second one took a little bit more energy, and the third one, well, are we going to remove a third electron? Oh yeah, we are. Because what does everybody want to be like? Everybody wants to be like a noble gas. which means a full S&P on your uppermost occupied main energy level. If we take off one more electron, and we get to aluminum 3+, and this is, by the way, the ion that aluminum forms, sort of in the wild. You got 13 protons pulling on 10 electrons. Is this even close to a fair fight? No. But more to the point, you have just taken everything off of that uppermost main energy level. You've totally removed the electrons from the uppermost main energy level. And now, what does aluminum look like? Well, it might help if we drew the noble gas notation for aluminum. So what noble gas would you use in the notation for aluminum? Neon. So aluminum, before taking off any electrons, was Ne 3s2 3p1. And what did we do here? We zapped that. And what did we do here? We took that down to 1. And what did we do here? We got rid of that. So by the time we get to here, we are looking at something that looks just like neon. What does every element want to be like? A noble gas. It has now reached its most perfect, most ideal form of existence. So the metaphor for me is a summer day that's 70 degrees. I have an awesome, really long book that I'm reading and a pitcher of icy cold lemonade in reach and a hammock. You're not getting me out of the hammock. It's not going to happen. You're not going to get aluminum beyond this formation. It will not happen. So what do you think happens to the ionization energy when we get to here? So we went up a little, up a little. What happens now? Go ahead. You know you want to make the noise with me. Come on. Pew, pew, pew. Oh, come on. You people are pathetic. Seriously. I have no problem making a fool of myself. The least I can ask on a Tuesday morning is that you embrace your foolishness. No? It's so hard. You'll make noises, huh? Okay. So, when we get to noble gas notation, guess what happens? You have a huge jump in ionization energy. So, every time you've removed an electron, the subsequent IE, removing the second or the third or the fourth electron, the ionization energy goes up. It takes more energy to get those subsequent electrons off the atom. Because now you're not taking an electron off a neutral atom, you're taking it off a positive ion. And when you get to noble gas configuration, the ionization energy absolutely goes through the roof. And that's one way to tell when an ion has reached noble gas configuration. When you look at the amount of energy that it would take to remove another electron, and there's a huge spike in IE, oh, you must be at noble gas notation, or at noble gas configuration, I'm sorry, not notation. Now, when we go down a group, so let's go ahead and look at group 1. What's the top of group 1? Put your finger on it. Okay, so we're looking at group 1 here. How many energy levels are between the nucleus and that outermost electron? 1. Not too hard to, not too shielded. So pretty well held on to by the nucleus. Can you get that electron off? Yeah, of course you can. This wants to be like a noble gas, so you can definitely pull that electron off. But, it's not all that, it's not all that shielded, so it's fairly well held. Okay, let me copy that. Let's move down one. What do we have? Sodium, right? 11 electrons, Gesundheit. 11 protons, starting off with 11 electrons, neutral. oops, let me copy this energy level, paste. So we have one electron out there on the far ring. How many energy levels between the outer valence electron and the nucleus? Just hold up your fingers. How many? 2. 2! So a little bit more shielding, a little bit easier to pluck off. What if, whoops, how did I do that? Copy, paste. What if we go down one period? What do we have there? What do we have? What do we have? Come on, put your finger on it. What's one period down from sodium? Potassium. 1, 2, 3, 4, 5, 6, 7, 8. Okay. How many energy levels between that outer valence electron and the nucleus? Hold up fingers. Come on, you can do it. 3! It's got that single valence electron out on the 4th main energy level. There's a lot of shielding between the nucleus and that outer electron. Do you think this would have higher or lower ionization energy than sodium? Would it take more or less energy to pull that outer electron? Less. As we go down a group, we tend to see ionization energy decrease. So the further down the group we get, the lower the ionization energy tends to be. If you grab your periodic table, you should all have it out because we've been working with it for quite some time now. I'm going to give you 3 elements: strontium, magnesium, and calcium. Put them in order of decreasing ionization energy. So from, decreasing. So from highest IE to lowest IE. And in your groups, go. Everybody has come to agreement within their table. So Pacific Northwest, my guys in the back, which one of these would have the highest ionization energy? Which one? Magnesium? Okay. Does everybody agree with that? Okay. Which one would have the next, which one would be the step down, would have slightly lower ionization energy? Great Plains. What do you think? Calcium, does everybody agree? Okay. Which one of these has the lowest ionization energy in its group? Old South. Yes, I guess there's not much left, is there? Okay, well that was kind of anticlimactic, I'm sorry. Yeah, so because this has got fewer, it's got less electron shielding between the valence electrons and the nucleus. So those outer electrons are more tightly held. By the time we get down to strontium, this is like the family I talked about with 13 kids. I'm not sure if Mom ever knew where kid 13 was. Too many kids in between her and kid number 13. So as we go down a group, we tend to see decreased levels of ionization energy, which means these things tend to be more what? If you're more willing to give up electrons, you tend to be more reactive. Okay? And in general, what we see is that reactivity increases as we go down groups. Okay, so now we're going to talk about one more concept. And I'm going to give you a little bit of time to do homework, and then we'll pick it back up. Actually, okay, tomorrow is Wednesday. The goal is that we are grading homework Wednesday, right? We'll see. I'm just going to see where we go. Okay. Ionization energy is taking an electron off of a neutral atom. Is that the only way to make an ion? No. We can add an electron to a neutral atom. And there are some atoms that would actually prefer to get an electron than give one up. So it's not as cut and it's the the wording here is vague. The energy change for adding an electron to a neutral atom is called electron affinity. What does affinity mean? What does affinity mean? I have an affinity for chocolate chip cookies. I like them. Obsession? No, not quite. Though I do like them. I can't be trusted around chocolate chip cookies, but I wouldn't go so far as to call it an obsession. I like them. I have an affinity for camping. I like camping. When you have an affinity for something, you like it, you enjoy it, you seek it out. Electron affinity is kind of like how much love an atom has for an electron. So we talk about the energy change, and it doesn't even, etymologically, like in terms of word usage outside of chemistry, the idea of calling an energy change an affinity doesn't make any sense, but that's what we got. Chemists are not English majors, so this is what we have. Electron affinity is a little tough. There are some atoms that want to gain an electron. The halogens. What would the halogens have to do to be just like a noble gas? Gain one electron. They're just like a noble gas. They would prefer to gain an electron. There is no way you're going to get them to give up electrons. It just doesn't happen. So if energy is released, let's just read those next two bullet points and see how little sense they make. If energy is released when an atom accepts an electron, EA is considered a negative number. If energy is absorbed, the atom is forced to take an electron. EA is positive. EA positive atoms are unstable. So here's what I want you to think about. I want you to think about this in terms of a hill. You might want to draw a hill, actually. And I have a rock on this hill. This rock represents some atom of something, neutral atom. This hill is sort of potential energy. So you've had experience with hills, you've had experience with rocks. You know what happens if you take a rock and you put it at the top of a hill and you let go and there's nothing between it and the lower level. What happens? It falls down. Gravity wins every single time. So things that are a rock sitting at the top of the hill, is that stable? Like if you've got a rock, just like a nice round boulder sitting at the top of a cliff, do you want to set your picnic up underneath that? Not if you value your skull. Car with no parking brake. Shaky transmission. Parked at the top of a hill. Do you want to take your foot off the brake? No. That's not stable. Things that have very high potential energy, and in those cases what we're talking about is gravitational potential energy. This is a physics concept from physical science. You should have talked about gravitational potential energy. But you get that. Things that have super high amounts of gravitational potential energy are typically not considered all that stable. Because at any moment they could fall and cash in all that potential energy, turn it into kinetic. Woohoo! Being at the top of the first hill on a roller coaster. High potential energy. Not real stable. Atoms are the same way. So the electrons that they have, their electron configuration basically creates potential energy. And if they lower their potential energy, they become more stable, just like a rock on a hill. Once this rock has rolled down to here, is it stable? Oh yeah, it's way more stable. It has lower potential energy. We have lowered its potential energy. What if we take this rock from here and we actually shove it up to here? Does it have lower or higher potential energy? Higher. Is it more or less stable? less stable. It's got more potential energy to cash in. It can get more speed going. So when we take an atom like fluoride, there, and it would be quite happy to accept one electron and become just like a noble gas. When we give fluoride that one electron, guess what happens to its potential energy? So now it is F1 minus. It has lower potential energy. It has lowered its potential energy. So energy was released. Because from here to here, there is some amount of energy, yes? Where did that energy go when fluorine lowered its potential energy? Out into the world. Poof, out it goes. Energy was released because the thing in question has lower potential energy when it's done than when it started. So energy was released, and we say that this is negative electron affinity. So this would be negative EA. Let's take a slightly different scenario. Copy, paste. Let's get rid of these guys. And let's not make this fluorine now. Let's make this sodium. What does sodium have to do to lower its potential energy? How does sodium end up being just like a noble gas? By doing what with electrons? I'm just going to hold you for a minute here. Sodium would have to give up an electron to lower potential energy, right? So if we took sodium and we actually forced an electron on it, and we had sodium 1 minus, is that more or less stable than a neutral sodium atom? Way less stable. Way less stable. Has anybody here ever held a spring down with your thumb? What happens when you let go? Boing! What we're doing here is holding that electron onto sodium. Metaphorically, of course, because we can't actually see a sodium atom, let alone hold an electron on it with our thumb. But metaphorically, we are pushing that electron down onto sodium. It's not stable. The minute you let go, what happens? That rock rolls right back downhill. This is positive electron affinity. Totally unstable. Can't be maintained. Cannot be maintained. Okay, we're going to stop there. I'm going to give you a little bit of time to do homework, catch up on problems that you need to do, and then we'll come back, we'll pick up on a few last concepts.